Hey guys, just wanted to do a quick lecture on deserts and how wind and wind erosion carve deserts and basically make the landscapes that are so familiar to us in our television programs and movies and even our cartoons from when we were a kid. Here we actually see right here on the screen some prototypical desert scenery, right? The rocks, the red rocks sticking up out amongst the sand and some clearly hardy but not very edible plants growing out of this sand. This is not a very hospitable place, but it looks like a kind of a fun place to hang out. This is what kind of we think of as being deserts. This is a scene that is actually quite explainable by science, and using the methods that we've been talking about sedimentation and erosion, we'll be able to explain all of these things that we see here in this image. So anyways, we're going to have a nice little discussion about deserts and wind. I think you're really going to like this. You're going to see some really beautiful images as we go forward. So make sure that you stay tuned in for that. All right, so let's jump in. So deserts are something that we usually consider to be a dry climate. And we don't normally think of deserts as getting a whole lot of water, or if they do, very, very small amounts, or it's in types, or the water arrives in a form that is not very usable to the plants, like fog or something like this. So we're going to go ahead and start defining why, or describing why these environments might be dry as we would define it. So what is meant by dry? Well, a dry climate is one in which yearly precipitation is not as great as the potential for evaporation. In other words, it's easier to dry things out than it is to rain things in. Right? It's kind of the opposite of a rainforest. It's really hard to dry things in a rainforest, but it's really easy to rain on it. So you get the idea. It's kind of the flip side of this. Dry regions cover 30% of our surface. So this is a substantial environmental circumstance that seems to happen on the Earth's surface. So here we see them in North America. We find them all across, of course, North Africa, famously into the Middle East. So this is where a lot of the famous oil deposits are. We got the Gobi Desert up here in Central Asia. And then, of course, we also have our the Kalahari Desert down here in South Africa, as well as several deserts here in South America. Now, what do we have over here? We have, of course, the Amazon rainforest basin on this side. So why do we have rainforest over here, but we have deserts over here, which tend to be kind of opposites? We're going to explain that as we go forward. So two water-deficient climatic types are commonly recognized as the desert regions, which are arid, meaning really, really dry, and which are more dry, I should say, than steppe or semi-arid regions. When we think of steppe regions, we should be thinking of things like big grasslands, big grassy fields. Kind of typical steppe regions that are famous as this area to the north here in Asia. This is the famous Mongolian steppe that you've read about in your history books. This is what gave rise to the famous Emperor Genghis Khan. There's typical steppe regions over here in Ukraine and up into Russia, as well as what we could classify as steppe up here in North America. So what causes the distribution of dry regions so close to wet regions? You know, it just kind of hinted at that with the Amazon rainforest or the deserts we see in South America, the Atacama Desert, for example. Well, the subtropical deserts and steppes, well, they lie between the tropics of Cancer and Capricorn, 30 degrees north and 30 degrees south. Let's go back to this previous image, right? Notice that the Tropic of Cancer and the Tropic of Capricorn are located at these two positions here, and the deserts seem to be clustered along these lines. Okay, there's exceptions to this rule, but for the most part, we find them clustered right here. We don't find them here in the middle, at least not much. We don't find them here along the equator all that much. Okay, just keep that in mind, right? So the basic cause, or the way that we think of this, is that there are regions of high pressure, sinking air that is compressed and warmed. It's a little more sophisticated than that. And what I want to do is I want to cover something called the Hadley cell. The Hadley cell is the idea that the equator, which is on average right directly beneath the sun, of course it varies as the seasons occur, but on average, we would say this is kind of the center part, And so we get the most direct sunlight at this location. If there happens to be water here, it gets hot, it's moist, and it tends to rise because hot material is less dense, than cold material, and it rises on up. And as it rises up, basically things start to decompress, it starts to cool, the pressure starts to change, and it starts to rain out stuff. So we wind up getting a lot of rainforest right along the equator because it rains right here at this position. Okay, so this warm, moist air rises, it dries out, it becomes very, very dry, and while it's up here in the upper atmosphere, it cycles up and over, and as it's up here, it cools off, and then it begins to sink because it's, of course, more dense at this point. And as it starts to sink, it drops in right at about 30 degrees north and 30 degrees south. Those are right adjacent to the tropics of Cancer and Capricorn. Okay, not far from them. So here we see that these cool, dry zones dry air will fall into these zones here, which is where we find our deserts. It begins to heat up, we get that warming occurring again, it starts to moisten up, and then it goes right back up. Now these arrows over here are showing the location of trade winds, which occur because the Earth is spinning underneath this Hadley cell. So while this circulation is happening, the Earth is spinning underneath it, and this gives the appearance of wind currents that we see between 30 degrees north and 30 degrees south on our globe. Okay, that's what we call our trade winds. All right. So basically, this can all be explained using a simple Hadley cell. This phenomenon is called a Hadley cell. There's other cells. It's usually we describe 3 of them. We're only going to concern ourselves with the one between 30 and 30. All right, so let's start talking about the different deserts and steppe environments that are a consequence of this. So we have West Coast subtropical deserts. So talking about these ones here. So here's the west here, okay? So cold ocean currents cools air and prevents it from rising, right? So the air there it's cool and it's dry, but because it's so cool, it can't rise. It can't actually reduce its density and rise up, okay? So the consequence is that you wind up, instead of with a rainforest arrangement, you wind up with a really foggy area. A typical example of this would be the Atacama Desert, which again is located right here on the Tropic of Capricorn, right adjacent to the Amazon rainforest, right over here, okay? Actually, the Amazon is located up here to the north, but you get the idea. Very close proximity. Okay, and this is what that desert looks like right here. This is the Atacama right here. You can tell this is a dry and desolate place. Very, very dry. Okay. There's also other examples of deserts that exist in other locations as well, away from the 30 degree to the Hadley cell influence, I should say. These tend to be sheltered in deep interiors of large land masses. The Gobi Desert, for example, in northern China and southern Mongolia, that is actually the border or the geographic border between these two countries. Basically, it's far removed from any ocean moisture. Basically, it's hard to get water into here, okay? And you wind up with a dry environment. There's some other reasons why we see it as well, but the sheltering or the distance from water is also a major reason why you will get a desert to form. Okay, and here's a picture of the Gobi Desert right here. I myself have actually done work here in Central Asia, right outside of Ulaanbaatar, just to the north, and this is actually a nice grass region from Ulaanbaatar all the way to the Gobi Desert. It's a famous steppe region, and yes, in fact, the capital of the Mongolian Empire is located right here. All right. So another way that we can get deserts to form, so we've talked about having it removed far away from water sources. We've had other places where the water cools the air so much that the air has difficulty rising and transporting that water into a location. Another way is mountain barriers, okay? So as air rises over a mountain, clouds form, releasing precipitation on the windward side of the island, or of the mountain. So usually I use the example of the Hawaiian island, which I will use a photograph here in a moment. So forgive me for saying island, but yeah, mountains. So here you can see that we have wet, moist air coming in, it tends to head up over this mountain and it rains out. You get clouds forming on one side and then it's dry on the other side. So this is the example of what we see in California into Nevada is on one side you get beautiful forest, famous the Coast Range, which has beautiful forests, and then you get over it, you wind up in the Great Basin deserts of Nevada and Utah. Okay, so these are examples here. Air flowing over the leeward side of the mountain is dry and forms a rain shadow. In other words, the water is rained out right here. You get beautiful rivers that start to come down the mountains on one side, but not necessarily on the other side, right? Leeward means the back end or the back side. Examples include the Basin Range and Hawaii's Kona Desert. So this would be the Big Island of Hawaii here to kind of demonstrate this point. Typical trade winds are coming in from usually the east to the west, not always, but typically the winds are coming in 90% of the time. This is the city of Hilo, located right here. Kilauea is located right here, which is an active volcano. And then, of course, the famous Kona Coast is located right in this zone here, kind of right here. And right here, as I'm delineating this area using the pointer, this is Mauna Kea. This is the Kona Desert. There's actually a desert here, and in this desert, there's cactus. Typical plants that you would expect to find in a desert. Okay, the reason why this happens is you get moist, wet air coming in off the Pacific, hitting the northeastern edge of the island. Lost my pointer there. Hitting the northeastern edge of the island up here, and as it tries to come up over the island, it rains out, right? So you get the water falling only on one side, and then as it comes over the other side, it's now dry. As a matter of fact, it has the potential to soak water up because it's now dry. And so this is the high point here. It gets over, and now it's a dry area, and you can actually see where that transition occurs right here, where it goes from green to brown. The city of Waimea or Kamuela is located right, I believe right about here. And you get the idea is you could actually have a town on one side that's in the wet zone and another one that's in the dry zone. And in fact, the city of Waimea is divided that way. Anyway, the famous coffee farms of the Big Island of Hawaii are located down here in the wet area here. But if you go up too far to the top, towards Mauna Loa, you will have difficulty growing anything. It's, again, a desert. Some people point out this area here. They say, I see green here and I see green here. Here's Kilauea, but why is there a big desert environment there? And there is, in fact, a desert or a pseudo-desert located there. The reason why that is a big brown patch isn't because it's not getting rain. It's actually getting just as much rain as the rest of these green areas. The reason why this is a brown patch is because Kilauea is spewing toxic fumes that actually kill the plants off and subdue the vegetation in the area. So it looks and acts just like a desert. And in fact, desert plants probably would do quite well there because you need something that is tough enough to deal with that environment. But the reason has nothing to do with the climate. It has everything to do with the volcano that's located literally right where that pointer is. Okay? And down here is another active vent of Kilauea called Pu'u'o'o, which has been active since the early 1980s. All right, so needless to say, the processes that we've been talking about in all the other environments in many ways apply to desert environments as well, but deserts tend to put their own spin on what is happening. So we're going to talk about these things. Weathering, for example, if you haven't figured out by now that weathering is absolutely fascinating stuff and it results in the most amazing landforms, then you haven't been paying very close attention. And in the deserts, it's no different. First off, mechanical weathering is more prominent than in humid regions, right? In humid regions, you have lots of water that's coming in all the time, and you get chemical weathering. In desert environments, you don't get a whole lot of water, and so therefore you don't get a lot of chemical weathering. So whenever it does rain, you get large amounts of physical weathering. But that doesn't mean that chemical weathering doesn't happen. It does happen. Some chemical weathering does occur over long spans of time, and it does produce clay, some thin soils, and oxidation of iron-rich sediments. Now, if you guys remember what iron oxide is, or oxidation of iron is, it's rust. It tends to turn things red. So deserts tend to have a red color to them. That's what this picture here is showing you. In fact, there's a flash flood occurring And you can see that it's washing a lot of this iron oxide rusty material with it down this gully. All right, so the role of water is extremely important, right? By definition, a desert is defined by its relationship to the lack of water. So most stream beds are dry most of the time. They're called ephemeral streams. So ephemeral streams only carry water in response to specific periods of rainfall. So here we see water carrying all kinds of iron oxide, basically weathered material, soils and stuff here in this desert. This is actually, I believe, a picture from Arizona. You can see that it's taking this milkshake color, it's coming down, but it's scouring it out, and then once it's done, it'll go completely dry again. Okay? And when rain falls, most of it flows as runoff into the stream bed. So almost everything finds its way to these stream beds rather than soaking in. The reason why, there's many different reasons why, but one good reason why is because you have very thin soils, right? And you have clays, and so these things are really poor for soaking in water, so it tends to run across the surface, especially if you get a really heavy rainfall. It can't absorb it, and as a consequence, it runs off. So you get the idea. What I really like about this is you see this the stream coming in here, and you can see a past flood event where we can see a car has actually been, and some junk parts have been picked up by the river and deposited here in one of the flood banks off to the side here, and there's also junk down here as well. This kind of should give you some idea of how powerful these flash flood events are when they do occur. You know, it could pick a car up and it just puts it into the deposit like it's a boulder or a stick or anything else, right? Floods don't necessarily see humans as anything special, and I think this kind of demonstrates the power of just this very basic flood event that's happening. I believe this happened in 2003. Here's a typical ephemeral stream that we would find in the, I believe this was a picture of the Mojave Desert. Here we see you know, boulders and cobbles and stuff strewn around with sand. And you can tell, obviously, this is an area that gets water from time to time, but it doesn't have any water right now. So this is a typical ephemeral stream that we would see in North America. What makes it different from the kinds of streams we would find, say, in Africa, is that African plants have not evolved as strongly the ability to live in deserts as we do see in North America. So we find things like cactus and these types of shrubs living in the desert environment, whereas in Africa, we don't see that as much. And as a consequence, we have dune fields, right, where almost nothing can live because those animals, or I'm sorry, those plants haven't quite evolved yet. So anyways, just wanted to bring that up here. This is a typical ephemeral stream. You probably wouldn't want to build a shack or a house or anything like that here, because if a flash flood were to hit even in these mountains, you might be in trouble. In fact, actually, the water seems to be coming towards us. We're looking upstream. And the reason why you can tell right away is the combination of these two streams coming down here below in this braided ephemeral stream bed. Anyway, sorry for the digression, but you get the idea. There's certain things that geology is always giving you clues as to the history of things. Okay. Here's another ephemeral stream that's been used by people for driving their trucks and stuff on. This is another picture also again in the Mojave Desert. Different names are used for ephemeral streams in various regions, right? In the United States, we use the word wash or arroyo. Arroyo is, of course, a Spanish word. In Arabic, it's a wadi. So in north of Africa and Saudi Arabia, it's called a wadi. This is actually where we get our English word water from, or it's a similar derivative, I should say. Donga is the South American phrase for this, and nulla is the word for these washes in India. Okay. And they're amazing in terms of their ecosystems, right? So here's a wadi, or let's say a wash, in its usual dry state. This is in North Africa. It's dry, it's dead, and all of a sudden, after our little rainy period, we get vegetation that sprouts right up, right? So you get a little bit of water in the desert, and all of a sudden the vegetation just pops right out, and you can start to see it. Beautiful, right? And in fact, this is a place where if there was persistent water coming through here, you might even think about setting up a grazing operation. And in a lot of deserts, there's considerable competition for regions like this for grazing. All right, so we've been talking about what gives rise to a desert, right? The types of precipitation, how the rivers work, how the washes operate. We're going to go into detail as we go forward, but in order to understand why these things are important, we need to talk about how desert landscapes evolve. Where do they come from? Of course, obviously it comes from the climate, but what is the result? What starts to happen as a consequence? Well, we have a couple of things that we need to bring up here. So arid regions typically have interior drainage. In other words, they drain into itself because the intermittent, or ephemeral is a better way of saying it, the ephemeral streams do not flow to the ocean. Erosion occurs without reference to the ocean. So remember, when the beautiful thing about the ocean is that rivers are always trying to cut down their baseline, right? If you recall our discussion on surface water several lectures ago, we talked about baseline erosion, right? In the case of deserts, that you can throw that right out the door, right? Because the water's not trying to get to the ocean, because a lot of that water just winds up evaporating or disappearing into the groundwater system. It never makes it to the ocean, okay? So there's an evolution that tends to happen over time in a lot of these deserts, right? A lot of times these deserts are a consequence of active uplift, the uplift of mountains. And of course, running water erodes and transports materials to the basin. So you get uplift of a mountain. In this case, here's some mountains. This is the Valley of Lakes in Mongolia. We see, which is actively deforming right now. Mountains are going up and valleys are going down. Here we see these mountains rising. Here's another mountain rising. Here's another mountain belt starting to rise, and some more over here. And in between them, we have a series of valleys with large lakes that have developed into them. And notice that all of the streams, in this cases, most of them are dry. Here's a wet one right here, but these are dry right here. These ephemeral streams are going into an internal drainage, right? There's nowhere for it to go. So where's the sediment going? It's going into the valleys. It's actually filling the valleys up while they're forming, right? So it's a competition between whether tectonics is able to open the valley up fast enough, or whether or not that same activity, the erosion, is going to fill it in, okay? And that's what winds up defining that balance, defines how deserts evolve over time. And we see this beautifully demonstrated here in Central Asia, in Western Mongolia. Okay, so let's show this in a probably more traditional example, which is the basin and range area of southwestern United States. So southwestern United States, this is the basin range, goes all the way from West Texas all the way up into Central Oregon. And there's a bunch of mountains. They're basically all parallel. They go north-south on average. And they've been pulled apart. Basically, it's a bunch of normal faults that have extended the area apart. And the United States has, in fact, been pulled to the west, right? So this area was more compressed at one point in the past, and it's now pulling apart. And we don't want to go into any more details than that. If you take a more advanced geology class in the future, you'll learn all about basin and range. With that said, so this would be kind of an early stage, right? You wind up rotating the mountains up. So the mountains go up and the valleys right next to them. So as we're pulling things apart, the normal fault rotates things like this and starts to pull them apart. So we get a nice valley in the middle, and you wind up with a mountain peak over here. And this is what this is demonstrating here. We get stylus, there it is. Here we have these mountain peaks forming edges right here, and then next to it a relatively deep valley, another edge, deep valley. And of course we do in fact see deep valleys and high ridges here in California. Right here's the Sierra Nevada, which is one very large example of this right here. Sierra Nevada is a huge block of material that has been uplifted through extension of always. And right next to it is a very deep valley. In fact, Death Valley is located right down here, about where this arrow is. So here's the kind of the tallest peaks of North America within the United States. And then right adjacent to it right here is the lowest point in all of North America, Death Valley. All right, so this is where the most active tectonics seem to be happening now. But that doesn't mean it's not extending all the way over here into western Colorado. Well, certainly is, or I'm sorry, into western Utah. Okay, so what happens? Well, as these things rise up, you wind up forming these alluvial fans. We've talked about alluvial fans in the past. We're going to be bringing them up again here over the next couple of slides. But basically, the alluvium starts to wash material into the valleys. And over time, the, uh, the alluvial fans start to really dominate the sides of the valleys, the main landscape. It starts to fill it in. So you notice the fill here is getting deeper, so the valley fill is deeper here. And eventually the valley fill can get so deep that the only thing that sticks out of the top are the very peaks of these remnant mountains, right? Just the tops. And so the tops of these mountains here are called inselbergs. All right, let's show some examples of these features as we're going. Well, we'll show some features, I'm sorry. So sediment-laden rivers from sporadic rains deposit debris at the mouth of a canyon. We've talked about these are alluvial fans. We've shown these in previous videos, so I'm not going to spend a whole lot of time talking about them. This is an image taken from radar I believe in this case it was an aircraft that flew over. Here we see the alluvium is being moved out. It's a combination of rock and water that comes out during major storm events. And basically what defines the edge of the valley winds up being a coalescing or a braiding together of alluvial channels or of that material out onto the valley floor. And that apron of alluvial fans is something called a bahada, right? A bahada. Now, in terms of the material distribution, we find that the finest stuff goes to the edge and the coarsest stuff falls out here way up near the mouth of these things. So there's a distribution aspect. And of course, we would expect that because water is going to have the highest velocity coming out of the channel and the lowest velocity down here at basically at the dry lake or the playa. And the consequence being the heavy stuff's going to fall out here, the light stuff's going to fall out over here, and we get a gradient that will form. Okay, and so this is a bahada, the coalescing of these two. What is this down here? This down here is actually a dry lake. This is a dry lake bed, and I believe this is a picture taken of the Pavement range in eastern California. Not too, it's just adjacent to Death Valley. So this is a dry lake down here. Okay, so I mentioned a couple of words that I haven't used before. One of them being a playa or a dry lake, right? So I've used both those terms now. And let's go ahead and describe what these things are. So during heavy rainfall, streams flow across the bahada to form a shallow, short-lived playa lake. So a playa lake is the dry, flat lake bed left after the water evaporates. And it's called a playa. Okay, so here we see this mountain has gone up, this mountain has risen up here, and here we have this valley fill that has come in. And here we've seen a major storm event. This is a place called Deep Springs in Eastern California. Eastern California is the best place to get images and to go study these events. And here we see that the lake has filled in. Now this lake is quite large. You can go all the way across it, but quite frankly, at its deepest point, it's probably no more than 3 feet deep. It's quite shallow. Over here we have a shoreline that is actually the old lake. The lake used to extend, of course, all the way over here where the white zone is. And we find deposition of evaporites like salt and things like this right here along the shore. And so basically this is the event of a major storm that's come in, washed in. And it's kind of a one-time thing, but it's brought in all these sediments and then the water is basically going to disappear, either into the groundwater system or through evaporation. So continued erosion diminishes the mountains to a few isolated bedrock knobs called inselbergs. So basically what's up here is trying to get down into here, right? The earth doesn't like really large holes and it doesn't like really deep holes or really high mountains. It's trying to always level things out. Take things that are high and put it into the areas that are low. All right, so I hope you kind of get an idea that the climate is working with the geology to produce these desert environments. That you got this internal drainage, alluvial fans coalescing to form, and in between those are dry lakes. Incredible scenery and science occurs in these places. It's a great place for geologists to go and learn how to be geologists because deserts, quite frankly, don't have a lot of vegetation. You can see the rocks very cleanly. It's very difficult to do this in, say, a rainforest because the trees and the brush and the bushes tend to cover everything up. You can't see any of the rocks. So anyway, you get the idea. So now that we've talked about how these things form, let's talk about how sediment moves through these things. Now we've talked about alluvial fans already. We're going to go actually into the aspects of wind. We've been talking about water a lot, and there's a perception, a general perception, that wind is also very good at transporting sediment, and in some cases it is actually quite good. One thing that it is not good at doing is wind is very poor at weathering. All right, so we need to keep that in mind. Compared to water, wind is a terrible, terrible agent for weathering. So let's go ahead and talk about what wind in fact does do in these desert environments then. So wind is less capable of picking up and transporting coarse materials. It doesn't have a whole lot of density to it compared to water. Wind is not confined, however, right? It's just different from water. So wind is not confined to channels. It can spread sediment over very large areas. It can even spread it across the ocean, right? It doesn't necessarily need to be down low near the ground. It can take things very far. And we can see this example here. Here's a sand dune. This is Sahara Desert. And we see the wind is kicking this stuff up and taking it well off to the east. Or in this case, I'm saying east, I mean it off to the right. How does it do this though, right? Well, it's actually not that different than what we were describing about water, right? So there's a bed load. We've talked about bed loads before with water. Again, if you haven't any recollection of our discussion of bed loads, go back and watch our video on surface water where we talk about these things. The bed load is carried by wind close to the surface. It consists mostly of sand grains, right? So here we see sand grains hopping along here. Sand moves across the surface in a process called saltation by bumping and skipping. So basically the wind, here's a nice diagram of this. Here's a sand grain. The wind comes through, it impacts the sand grain, and it motivates it to start basically hopping along. It doesn't quite suspend it. Suspension occurs when it gets up into the air and it doesn't bump anything along the ground. Or it could roll along or creep along, slide along the bottom here. Sand typically bounces. And you can do this experiment. You can, on a windy day, take some sand, throw it on the road or on some concrete, and you'll actually see it start to bounce, as it's moving along. It's an easier path for it than to simply roll. And this is, in fact, how we see sand grains move. Now, it usually doesn't, even in the worst of storms, sand, or coarse sand, I should say, rarely ever gets higher than 1 meter above the surface. If the wind is strong enough to motivate it to a height higher than 1 meter, then it's actually going to be technically in suspension at that point, and you're going to get sandblasted by one of these types of events. The suspended load is carried high into the atmosphere, compared to the what we were seeing over here in the bed load, where it only goes about 1 meter up. There's no limit to where this thing can go. It consists mostly of silt-sized particles. Surface area must be high compared to weight. Basically what it's saying is if you have something that is nice and flat, doesn't weigh a whole lot, but it's got a lot of surface area, it's really easy for the wind to pick it up and to move it. Hard to move fine particles unless they have been disturbed on the surface, right? So a classic example is a clay road with or without a car driving over it, right? So if you have a car driving over it, you'll see a big wisp of cloud coming behind it. But if you are looking on a clay road without a car, nothing will happen, right? So it has to be disturbed. Okay, the suspended load can be transported very far distances. We do, in fact, detect from satellite imagery dust from the Sahara Desert can reach all the way into the Caribbean Ocean, or the Caribbean Sea, off the coast of Florida and down to the south all the way to northern shores of Colombia. All right, so here we see a couple of examples of these things, a major dust storm blowing in. This is in, I believe, in North Africa. This is not something you want to get caught in. This is a dust devil. This is a playa dry lake down here, but this is a dust devil, which is basically a whirlwind. And the wind is just at that one location traveling so fast that it's able to pick up and suspend small particles and push it up into the air and can transport things quite long distances. There's Another phenomenon that is kind of neat to talk about, and they're called deflation and blowouts. So deflation is the lifting and removal of loose material, right? So the wind is going to be moving all kinds of stuff around based upon size and how, that weight to surface area ratio. Um, this type of stuff can be hard to notice because the entire surface is being lowered all at one time. So if you've got a farmhouse, you're looking out, things could be going down slowly through some kind of deflation. Um, and unless you have some reference material, everything's moving down, you won't even notice it. Okay. During the Dust Bowl, this was an event that occurred during the first half of the 20th century. It had a major effect on the economy of the United States and much of the world, actually. But during the Dust Bowl, vast areas were lowered by 1 meter in a few years. So in a very short period of time, that topsoil was reduced by over, in some cases, 3 feet, 1 meter. This is really not something you want to see happen. Deflation also produces blowouts, which are shallow depressions, and they can range from small dimples to depressions that are 50 meters deep and several kilometers across. So here's deflation, a deflation example here. Let's remove 4 feet of soil. So right where this gentleman's hand is in the image down to his feet, right down here, that's how much the soil has moved down. The reason why this clump is here is because the grass actually held through its root system, held the sand in place, so it couldn't be pulled away by the wind. But the wind was able to scour away everything else, and so this is all that remains. This peak and this peak here are all that remains of the amount of deflation that has occurred here. And so this is what kind of a typical blowout would look like in the illustration, right? You have these plants. The plants are protecting the soil right underneath it, but not around it. So you get these, pinnacles with the plants up on top. Another really neat feature of deserts is desert pavement. Desert pavement is one of those features in deserts that human beings have been taking advantage of for as long as we probably have been around. Desert pavement is a nice flat surface that comes about as a consequence of certain types of erosion. So most deserts have these, veneer pebbles and cobbles. They form from an initial surface of coarse pebbles. So here we have a bunch of coarse material mixed with fine grained material. The fine windblown grains are trapped between the pebbles, and they get wedged in there. They get concentrated. The larger pebbles get concentrated. And gravity and infiltrating rainwater move the fine sediments beneath the cobbles. In other words, it's constantly pushing the fine grained stuff down or blowing the fine grained stuff completely away. And so what does that do over time? It concentrates the desert surface into basically where you find nothing but a bunch of cobbles right at the surface with very fine-grained material that's kind of locked in between. And it makes a very hard crust up here on the top. You can walk on it, you can even drive your vehicle on it very, very easily. So this is kind of a typical desert pavement. This is an image taken in the Mojave Desert of California. You can see, here's the size of a foot. These are cobbles that are all in here that easily can walk across this. All right, so now we have an understanding of how this erosion occurs. Let's talk about the different kinds of deposits that exist then, and then we'll be done with this nice little lecture. I hope that you're enjoying some of the images we have in here. The first thing we're going to talk about are dunes, and then we're going to come to another type of deposit called a loess deposit, and then we'll be done with our discussion. So a dune is just mounds and ridges of sand from the wind's bed load, right? So it's the bouncing of the sand along in the bed load, and that creates dunes. And loess is extensive blankets of silt once carried in suspension. So in other words, things are picked up in suspension and deposited somewhere else where basically where the wind calms down and loses its energy. It drops that sediment. Okay, so we're going to look at these. So sand deposits, of course, when we think of deserts, you think of sand instantly, right? So sand will accumulate wherever an obstruction blocks wind flow, creating a dune, right? So if you have changes in velocity of wind, you're going to wind up either eroding not eroding, but picking up sand or you're going to be depositing sand, right? That's kind of the way the whole thing works. So dunes often form around a clump of vegetation or rocks, right? Because they obstruct the wind. So if you have a bunch of vegetation in the area, the wind breaks it up, or I'm sorry, the wind is broken up by the vegetation and the sediment drops out. Most dunes have an asymmetrical profile, right? You have a run-up zone on one side and a fall-off zone on the other. So, if the wind is coming up this way, it's dropping off on this side here. So the windward slope is gently inclined, and the steeper leeward slope, right? This is the far side. We talked about lee a little bit earlier in this lecture. The leeward slope is called the slip face. So in other words, we have kind of this inclined slope that comes up, the wind comes up over it, it might be picking up sand, and then it deposits it right on the leeward slope or the slip face. The slip face typically maintains an angle of 34 degrees, which is the angle of repose for sand. So if we put our protractor on here, it'd be about 34 degrees. Right? If it was at 35 or 36 degrees, it would start to slough off and we'd have mass wasting start to happen. So here's the structure of a typical dune then. So as sand is deposited on the slip face, layers form inclined to prevailing wind direction, creating cross-bedding. So here we see relative wind strength. It's lower here than it is up here at the top of the dune because there's friction with the earth, of course. So here's the windward face. The wind is coming in from the left here, and it's coming up over. You get saltating of sand, and then it falls or cascades down the front of the slip face at an angle of 33 to 34 degrees, the angle of repose, right? And what do? We wind up seeing that we have a nice bedding that occurs not in the same plane as the bottom of the layer, right? So the bottom of the dune is actually the bottom of the layer, but we have a cross bed that we see developing within the dune as it moves. So moving sand can be troublesome for permanent structures like roads and buildings. Yeah, dunes actually kind of walk right across roads all the time. It's kind of a major problem in desert areas. Let's look at some of this cross bedding. So here we see different kinds of cross bedding, so asymmetrical shape. But here we see cross bedding in rocks. These are sandstones in Zion National Park in Utah, and the famous beehive structures that we find when we go to Utah in the sandstones. All right, so here we see the dunes again. Here's a dune, here's a dune, here's a dune, and we see the cross beds located within the dunes. All right, I don't want to belabor this slide too much, but there's 6 different kinds of dunes. What they're really dependent upon is a couple of different factors. For example, vegetation. If you want, you can go ahead and pause it and read the captions we have located in here. But essentially, for example, between A, C, and E, we have transverse dunes as being the C, Barken dunes as A, and then we have another one over here. These are dunes that form these different structures, not because the wind is different, but because the amount of sediment is different. So here we see a very low level of sand. Here's an increasing amount, and so it evolves from A to C. And then here we see this type receiving more sand, and it evolves again into this dune field located right here. So the dune, it's the supply of sand that determines these here. These over here are determined by wind direction. So linear dunes, here we see dunes that are coming in. We got winds coming from 2 different directions, right? Perhaps on this Barken field. So you wind up getting linear dunes here. Okay, you got parabolic dunes and star dunes. Star dunes are really interesting because you have wind coming in from 3 different directions to form these different things. Most famous examples that I've seen of this are Kelso sand dunes in Southern California. All right, so let's talk about loess deposits. I believe I only have perhaps just the last slide and then we are done. So loess deposits are material that are basically deposited by storms over thousands of years, right? The wind comes along, it blows up a bunch of dust and it dumps it somewhere else. So sources of sediments come from deserts and glacial outwash deposits. Loess in China originates from desert basins in Central Asia, right? So, you know, what we find in one location might not be from where we expect it. So loess in the United States and Europe is the product of glacial material from way up north. Um, Fascinating stuff. Here we see a vertical bluff of loess that is, in this case, near the Mississippi River in southern Illinois. It's about 10 feet thick. Here we see an image of people actually building dwellings right into the loess deposit because it's actually pretty coherent and strong. They've even put some nice designs here to make it look like it's brickwork, right? Really cool. Okay. So anyways, I think we've kind of covered everything there is to say about deserts in a simplistic way. The different types of deposits, where they're derived from, where the red color comes from, what happens to the water, why is there no water? I think we've covered all those questions. So if you have anything that you want to add or any questions that you might have, by all means, send me an email and we will try and get right back to you about answering your questions. So until the next lecture, I hope you do well. See you next time.